This video shows how the equilibrium constant is affected by temperature in a quantitative way. Alright, our beginning step to determine how temperature affects the equilibrium constant is just the overall chemical formula that allows us to predict whether a process is spontaneous or at equilibrium, okay, which is this one. Now what we're going to do then is examine what the condition of equilibrium is, right? So at equilibrium what happens is that this reaction Gibbs energy is zero, and then what you have is that this equation takes place, right? Now the equilibrium constant is the value of the reaction quotient at equilibrium. Okay, so here we actually have a way that allows us to see how the equilibrium constant depends on temperature. If you solve for the equilibrium constant, what you get here is that this is equal to e to the minus delta RGM at the standard state over RT. You can take natural logs of this to see a little bit better what that dependence on temperature is, and you get to the following expression: delta RGM at the standard state over RT. Okay. So in principle, it looks that we're done, right? Because you have that the equilibrium constant depends on temperature in this fashion. But there's a little bit of a problem here, and that is that the reaction Gibbs energy also depends on temperature, right? So while this equation is correct, it's not all that useful. What we want to do is see if we can actually come up with an easier expression to use where we don't have to worry about the temperature dependence of this term right here. Alright, so to examine how this depends on temperature then, in an explicit way, what we actually do is take the first derivatives of that expression with respect to temperature. Okay, because that is going to tell you the sensitivity of this natural log of the equilibrium constant and ultimately the equilibrium constant on temperature. Alright, so what we have to do is just take that first derivative with respect to the temperature on both sides of the expression. Alright, so let's think about that right hand side. Notice that we can take a factor of minus 1 over r, right? That is going to be a constant, and that means that the first derivative is completely insensitive to that, right? So we take that minus 1 over r, and we just have to take the first derivative of the rest with respect to temperature, because those are the terms that truly depend on temperature. So then we have to take the first derivative of the rest, which is this reaction molar Gibbs energy at the standard state over temperature. Right, so that is delta RGM naught over T with respect to temperature. Right, that's how this works out. Now, of course, we recognize this term right away. Right? This is something that we have studied using the Gibbs-Helmholtz equation. As a matter of fact, that's what the Gibbs-Helmholtz equation allows you to do. Right? It tells you that the first derivative of the change in Gibbs energy over temperature with respect to temperature, right, that is simply minus the change in enthalpy, which in this case will be reaction molar standard over temperature squared. And again, this is the Gibbs-Helmholtz relation, which we have studied in a different video. Alright, so we can then make great progress here. So we can say, well, the natural log, also the first derivative of the natural log of the equilibrium constant with respect to temperature is going to be equal to, this minus sign is going to cancel with that one. So what we have here is simply going to be delta R HM over RT squared. Okay, so that looks like a much simpler expression, and of course to find an explicit dependence of the equilibrium constant on temperature, we just simply have to integrate this. Okay, so let's see if we can then do that. The first thing that I do is I'm going to separate terms. Natural log of K is going to be equal to the enthalpy of the reaction at the standard state, molar over RT squared, and then differential of temperature. Okay? Alright, so then let's take the integral of this, and we're going to do it using definite limits. So we're going to integrate this from a value natural log of K1 to a value of natural log of K2. So K1 would be the equilibrium constant at temperature T1, and then K sub 2 will be the equilibrium constant at a different temperature T2, and then the limits of this integral over temperature will be T1 and T2. Okay, so that is fairly straightforward. Notice that this is simply going to be the natural log of K evaluated from K1 to K2. So actually that simply turns out into the ratio of the natural log of the ratio of those equilibrium constants. Okay? All right, and then on the right-hand side, we have a few things here. Of course, we can take 1 over r, we can factor that out of that integral. So that's going to be 1 over r. And then an approximation that we're going to make here is to assume that the reaction enthalpy also does not depend on temperature. Now, we know that that is not exactly true because Kirchhoff's law allows you to actually establish how the reaction enthalpy or any change in enthalpy varies with temperature. Okay, so then the approximation is that this is going to work if the change in temperature is not very large, right? So if that difference between T1 and T2 is fairly small, so just a few degrees, then largely you can approximate that the enthalpy of the reaction is going to be quite constant, right? So under those conditions, then you can simply factor it out of the integral, and then you just have to integrate here 1 over t squared differential of t, right? So from t1 to t2, and that integral is fairly straightforward. This is just minus 1 over t evaluated from t1 to t2. Okay. All right, so then let's wrap up. I'm going to rewrite this so that this negative sign is going to be placed right in front of there. That is going to be the natural log of K2 over K1 is going to be equal to minus the reaction enthalpy at the standard state divided over R, and then 1 over T2 minus 1 over T1. This is called the Van Hoff equation, and I should remind you that Van Hoff was the first ever Nobel Prize in chemistry for work related to this, and specifically to osmotic pressure. Okay, so let's then wrap up. In this video, we have seen a way to quantify how the equilibrium constant changes with temperature. Okay, and it turns out that that is simply related to the reaction enthalpy at the standard state, and this is a number that is very easy to get from thermochemical tables where we have enthalpies of formation for a variety of species that might be intervening in a chemical reaction.